Before we take a look at any specific circuits, let's look at this block diagram here to get a better understanding of our feedback basics. So here we're going to assume we have an ideal feedback amplifier, and that means we're not going to be considering any loading effects. So ideal feedback amplifier, so no loading effects. And we're not going to be too specific in terms of what these signals are, so our signals can be currents, voltages, a mixture of the two, so we're not really being specific yet. Let's say V, I, or some mixture. And so taking a look at this, let's go ahead and label some of these signals. So you'll notice over here on the left we have our source, and so we could call this then between our source and our summing junction S sub I, and so this would be our input signal. We then have that going into this summing junction, and we see our input is being added. Our A here is our amplifier, and our A, our capital A, we're going to define as our open loop gain. So that's going to be an important definition to know. And you might also see this referred to as amplification factor. Okay, so A. And so basically after we've summed it, we'll kind of come back through this loop, but we say that this is going to be our output here. And so we notice that a portion of our output is going to some load. We said we're not going to be considering loading effects right now. A portion of the output is then sent through this beta, and this beta block is just multiplying. I'll have a note about the beta here in a second, but our beta produces this feedback signal. We'll call it S sub FB. So this is our feedback. And so note that this S sub FB is being subtracted from our input signal, and the resulting signal that's going to be fed into that amplifier A, we're going to call S sub epsilon, and that's going to be our error signal. Okay, so a couple of things to note then, like I just mentioned, because we have our error signal being produced from our feedback subtracted from our input, so basically focusing on the subtraction here, what we can say is we have negative feedback. And so as advertised, that's what we're going to be focusing on in this sort of unit here. Okay, one other thing to mention is that this beta term has a different meaning than what we've seen before in previous classes and even previous sections of this class. So here, our beta is something we're defining as our feedback transfer function. Okay, so feedback transfer function. So it's very important to note that this is not our transistor current gain. So if we do, for whatever reason, need to reference a transistor current gain in this section, what we're going to use is HFE. And so we're going to assume that our DC gain is equal to our AC gain with lowercase fe. So we're just going to use one general HFE. But very important to note that our beta is not equal to a transistor current gain in this section. Okay, so now that we've got sort of that straightened out a little bit, let's come back to this basic block diagram and let's do some analysis. So let me actually copy this and bring this down here so we can see it as we are discussing it. Just come down here to a new page and we'll just put that right there. Okay. So analyzing this, the first thing we can see, let's just write some basic equations here. We see that our output signal, SO, is equal to A times our error signal, S sub epsilon. We see that our feedback signal, S sub FB, is equal to beta times our output signal. And then the third basic equation we can see, which we described before, was our output signal, our error signal, S sub epsilon, is equal to the input signal minus the feedback signal. So we said that was the case because we have negative feedback. So now to be consistent with the notes posted on Canvas, let's go ahead and label these equations as 1, 2, and 3. So what we're going to do now is we're going to sort of combine these equations. So specifically we're going to plug 2 into 3, and then we're going to plug that result into 1. So 2 goes into 3, and then once we have that, we're going to substitute sort of that combination into our equation 1. And so what that gives us is that our output signal is equal to A times the input signal minus beta times the output signal. So pretty straightforward substitution. Of course, feel free to do that step by step if it's a little difficult to see all done at once there. So we'll call this equation 4. So now what we're going to want to do is we're going to want to rearrange this equation 4, and we're going to want to solve for a new term that we're going to call our closed loop transfer function. So rearrange and solve for our closed loop transfer function. And so our closed loop transfer function, so I'm making a point to be very explicit with how I define things here. Our closed loop transfer function is going to be defined as, given the symbol AF, and it's going to be defined as our output signal divided by our input signal. And so that's in contrast to just our A, which we defined up here as the open loop gain. So here our A with no subscript is open loop, and our A sub F is closed loop, because now we've used that beta branch to close the system. So rearranging equation 4, we find that this is equal to A divided by the quantity 1 plus beta A. And so oftentimes we'll introduce a new variable here, and we'll say this is A divided by 1 plus T. So this is going to be equation 5, and I've introduced a new variable here, T, and so we're going to define T is equal to BA is our loop gain. So a lot of new definitions, a lot of things to keep track of, so just make sure everything is sort of straight, everything makes sense, and you're not getting definitions mixed up here. For right now, we're going to assume that T is positive and real, and that's usually going to be the case for negative feedback. So positive and real for our negative feedback systems. Okay, so we've got open loop gain, we've got closed loop gain, we've got loop gain. So again, just be very careful. Make sure you understand well what each of these definitions means. Okay, so now we're going to take a look at this, and we're going to see how can we start looking into these advantages of our feedback, and where exactly does that come from. So we're actually going to look at 5 and 2 and 1, so equations 5 and 2 and 1. So combining these, what we're going to get is we can see that our T, our loop gain, is equal to AB, as we've said before. So that's sort of just from our equation 5. So now we're going to come back up here to two of these more simple equations, and we can relate this to our feedback signal and our error signal. So we can say this loop gain is actually equal to our feedback signal, SFB, divided by S epsilon. So again, if that's not immediately obvious to you, please feel free to go back and do that algebra. So now typically our error signal is going to be small. So we're saying typically SE, S sub epsilon, is small. And so what that means from this new equation here is that our loop gain is going to be large. So our T is large, since the S epsilon is in the denominator. So what we can say is we have T equals A beta, and let's say for the case of that much greater than 1, then our equation 5 can be simplified. So 5 becomes, and so if we come back up here to 5, and we're looking at this expression here, so we say if beta times A is much greater than 1, well, that's essentially just beta A in the denominator then, so we can say T is, and let me say this is approximately A over A beta. Well, of course, now we can just cross out our two A's, and we're left with just 1 over beta. And so let's call this equation 6. Okay, and so basically what we can see here from equation 6 is that our gain, or our transfer function of this feedback amplifier, is essentially only a function of the feedback network. So from this, we're saying that our gain, or our transfer function, of our feedback amplifier is essentially, so not quite because we made an approximation where we neglected that -1, but essentially it's only a function of the feedback network. And so we'll take a closer look at that diagram, that block diagram again, but we're saying it's essentially only a function of our feedback network. And we notice that's because this loop gain is 1 over beta, and of course our closed loop gain is then essentially just 1 over that loop gain. So we come back up here and we notice that the original amplifier gain, A, no longer appears anywhere in this equation for our closed loop gain, AF. And so that's what we mean by saying that this is essentially only a function of our feedback network. So one other thing to mention too is if we're assuming this large loop gain, so we're saying that A beta, which is our loop gain T, much greater than 1, what that means is we can also look at sort of this general equation 5 here, and instead of talking about our A sub f, let's look at it in terms of our output and input signals. So we can say our output signal is equal to A divided by 1 plus beta A times our input signal. And again, we can neglect that 1 in the denominator if our beta A is much bigger. And so we can say this is approximately 1 over beta Si. And so if we then go back and we plug that in to our equation for our error signal, we know our error signal is equal to our input minus beta times our output. So the second part here is our feedback signal. And so using that approximation, we see that this is approximately our input signal minus beta times our output, which we just said is approximately 1 over beta times Si. So of course these betas are canceling out, and we see that this is equal to 0. And so what that tells us is if we have a large loop gain, so a large T, means that our error signal is approximately 0, so really small values. So error signal decreases to almost 0. So in subsequent videos, we're going to take a little bit closer look at these equations and see how this affects our gain sensitivity. And then after we have a little better understanding of our basic feedback network, we're going to look at some specific circuits, both op-amp circuits as well as discrete circuits.